And here we go just one last time with sum and difference formulas. We've got where they came from. We've got how to use them in a very immediate sense, right? Evaluating the trig functions at very specific angles. So what we lack is tying that back into finding them useful in proving more identities, using them as a tool to solve equations. Because, as I mentioned earlier, not in the previous video, but a little before that, the main goal for the rest of this unit is going to be in solving equations, and actually a good bit in the next unit as well. Right, we are going to, this was just the introduction into analytic trigonometry. The entire point of all of the analytic trigonometry that we will look at for all of this class is solving trigonometric equations. Right now we've kind of got the training wheels in place because they always are identities right now, but we will move away from that once we are confident and comfortable doing so. Let me give you an example of how to use sum formulas or difference formulas in a proof of an identity. Here's a theorem for you that we're actually going to prove here. We are going to prove something together. And by that I mean I have something written up and you're going to follow along, and hopefully it makes sense to you, because if not, I need to know about it. The theorem states that if you have any of the 6 trigonometric functions, so say if your function is sine, then its cofunction, in that case being cosine, can be written as sine of pi over 2 minus x. If your trigonometric function is cotangent, then that cofunction, which would be tangent, we could write as tangent of x equals cotangent of pi over 2 minus x. And the theorem states that this is true for all of them. And so you can do this for all 6. We have one proof line out here for just the one. We're going to show that for cosecant, its cofunction, secant, can be expressed as cosecant of pi over 2 minus x. And here's how we're going to do it. We're going to start with the more complicated side, as we have been doing. We're going to write everything in sines and cosines, as we have been doing. And now we're going to apply an existing identity, as we have been doing. So cosecant is now 1 over sine. Having done that, we'll worry about what's inside the argument of sine. I see a difference of 2 angles, angle 1 being pi over 2, the other being negative x. I will then use my difference formula for sine, alternatively my sum formula for sine, accounting for the evenness and oddness of sine and cosine. So sine of pi over 2 minus x becomes sine of pi over 2 cosine x minus cosine pi over 2 sine x. Sine of pi over 2 is 1, that evaluates. Cosine of pi over 2 is 0, that evaluates. So now I have 1 over 1 cosine x minus 0 sine x. I have 1 over cosine x. I have shown cosecant of pi over 2 minus x is equal to secant of x. And it's going to be the case, and if you feel adventurous, or if you feel that you are majoring something a little more philosophical in nature, then maybe take the time and do another one. Maybe take tangent and show that tangent of x is always equal to cotangent of pi over 2 minus x. You would have to use the sum or difference formulas for cotangent, but you could do it. For all of us, though, I want to once again remind you of our basic strategies for proving identities. Start with the harder side, the side that's meatier, there's more to work with. Start with that side. Simplify that side down as far as you can go. If it helps, write things in terms of sines and cosines. And if it helps, or if you can, use substitutions using existing identities. Right now we have access to Pythagorean identity, sine squared cosine squared equals 1, its iterations. We now have sum formulas and difference formulas. We have even odd identities. And also, we just showed it, so why not also look at cofunction identities? Right? Every identity you have access to is something you can use to prove other identities. And the challenge in this class is not going to be in remembering the identities. It's going to be in deciding which ones to use. That's what I want you to focus on. That's going to be the bigger challenge to you in whatever you're going to get into. So that's what I want us to focus on in this class. And really, that's all I got to say about this as well. The remainder of accomplishing mastery for proving identities is purely by experience, right? I've given you the guidelines. I've given you the formulas and identities to use. Now you got to run with it. And in running with it, you can prove some pretty powerful things. Let me show you what I mean. One last quick example for us here. There's another theorem I want us to look at. And that theorem says that if you have a sine wave and a cosine wave, any two sine waves and cosine waves in the universe, you take them and add them together. And this can be a matter of signal processing, like you have two inputs, mic 1, mic 2 coming in, and the speaker system just combines the two electrical signals and plays the sum of them. Well, that will always be a sine wave or a cosine wave. And we're going to tackle that. We're actually going to show that here and now. The theorem states that you have some sine wave and some cosine wave being added together. The resultant sine wave is going to have some phase angle phi and some amplitude k. Note here there's an implicit assumption that the sine wave and cosine wave are in phase, they have the same frequency, and so on. This is a specific case. We're going to look at the general case, probably never. It's kind of a mess. If you come into my office, or if you're really feeling adventurous, you can look up the general proof for sine wave with some x plus alpha phase angle and some x plus beta phase angle here, but this is enough. So I got two waves being added together. They have some resultant amplitude, some resultant phase angle. And I'm going to go ahead and tell you the theorem in full. The amplitude is going to be the square root of the sum of the squares of the individual amplitudes, and the phase angle is going to have this stuff right here. And I'm just going to give this to you because now your job is to decide how to use it. Because our job now to prove this theorem is simply to show that a sine x plus b cosine x equaling k sine of x plus phi is an identity. And we have all the tools at our disposal that we would need to do that. We can use this substitution for k, this substitution for cosine of phi, and this substitution for sine of phi. We can use a sum formula, a difference formula, any other formula or identity. So take a second and decide what the plan of attack is. Just what we're going to do. Maybe not how we're going to do it, although if you want to stop the video and try it yourself, feel free. But you tell me, how are we going to go about doing this? What side are we going to start with? What identities are we going to use first? Let's go from there. And here's my plan. Actually, I spoiled it. Here's my plan. I'm going to wager that this side is more complicated than the other. Because I have a sum formula that's going to have to come up, I imagine. There's more to unpack on the right-hand side than there is on the left. So I want to start with k sine of x plus phi and turn it into a sine x, b cosine x, using this substitution for k, a sum formula for sine, and then after we use that sum formula for sine, I imagine these two substitutions will come into play. Let's see how it goes. So first of all, the sum formula for sine. That becomes sine, cosine, cosine, sine. Then I'm going to substitute sine phi and cosine phi, right? We had these substitutions. So cosine phi becomes a over root a squared plus b squared. Sine phi becomes b over a squared plus b squared. And k becomes a squared plus b squared. This is what we have now. We distribute that k value across. It cancels with this stuff and this stuff. So I've got sine x times a, cosine x times b. And would you look at that? In reverse now, we've turned a sum of two sine and cosine waves into a single sine wave. How about that? So let me write this up for us. Right, we have now added more identities. This is going to be exciting, right? We've added more identities, and we've used those to find exact values. In the next section, we're going to add more identities and find more exact values. Also in this section, we proved more identities. In the next section, we're going to prove more identities. What's coming down the pipe is a lot of new identities and a lot of new formulas. Right? You are going to have a whale of a time deciding which ones to use. Never in memorizing them, never in remembering what they look like, but in deciding which ones to use. But that's okay. We will worry about this in a while. We are going to spend a good chunk of time where we are right now, in just using the basic identities, using the sum and difference formulas, until we're comfortable with that. And then we're going to add more on top. So look forward to that or dread it. I am not going to tell you your business. I look forward to it. This is my favorite part of the semester. This and what we get to after this also when we get to polar coordinates. So I'm really excited for the remainder of the semester. This is where things really come into play, come into its fullness. So I'm excited. And I look forward to seeing you in the next class. You have a good rest of your day.